Welcome to our discussion of electricity. So we are starting this unit by starting to talk a little bit about electric fields and electric forces. So we're going to discuss what a charge is and then how we can use that information to figure out where a charge might go and how much force it might exert on something because of being in an electric field. All right, so this is chapter 20. Here we go. So let's start with this idea of a charge. A charge is either positive or negative, and a charge is conserved. So it's positive and negative are kind of made up concepts. There's nothing innately positive about a proton or a positive charge, but there are two different charges. They are opposite from each other. They repel each other, they attract each other, or if they're the same, then they repel. And we call one of them positive and one of them negative. We could also call them 0 and 1. We could call them 1 and 2, A and B, but we chose positive and negative as the general scientific convention. Okay, so opposite charges, a positive and a negative charge, are going to attract each other. So here's a positive charge, here's a negative charge. They both get pulled together. If I have two of the same type of charges, two positive charges, for example, or two negative charges, they're going to repel each other. So they're going to push away from each other. The force is against each other. Okay. So how does that work in the real life? Well, we have two objects here, wool and plastic, and initially they're neutral. They have an equal number of positive and negative charges, which we can see right here. There's pluses and minuses in the wool. There's pluses and minuses in the rod. There's the same number of pluses and minuses, same number of positive and negative charges in each of them. And so they're both neutral, so equal amounts. Then when we rub the plastic and the wool together, the negative charge moves from the wool into the rod. So there's this thing called the triboelectric series, and it says how much something is willing to get rid of its negative charges. So the rod wants to pick up some negative charges. The wool is willing to give those negative charges. What we end up with is the rod has a bunch of extra negative charges. It still has all its positive charges. And the wool now has fewer negative charges, but the same number of positives. So if we do like a how many versus how many, we see that the rod now has 3 extra negative charges and the wool has 3 extra positive charges. So this is what we would draw in our charge diagram. We're just showing the extra charges. So the extra pluses and the extra minuses in there. All right, so we can separate materials into two different types, conductors and insulators. Conductors is where a charge moves easily. So that might be something like metal, and we tend to use conductors for things where we want charge to move, like electric lines. Insulator is where the charge remains immobile, so it won't do a whole lot of moving through that insulator. This would be like plastic, and we tend to use insulators for areas where we don't want a charge to go through, like the covering on an electric wire. We don't want the charge to go out of the wire and into your house and start a fire, so you have an insulator around that electric wire. Okay, so looking at that, if I have a metal ball and some charged plastic, if I have them separated by a plastic rod, then the first metal ball over here can acquire the charge from the charged plastic, but this plastic rod serves as an insulator, and the second metal ball doesn't get the charge. It remains neutral. But if I connect them with a metal rod, the metal is a conductor, so the charged plastic gives the charge to this one. It is conducted across to the other ball, and so both spheres, both balls acquire that charge, right? So that charge would be split between this whole system of two balls plus a rod. All right, so polarization. Polarization is when a positive and negative charges are separated within a neutral object. So charge can move within an object itself. And so I have a neutral sphere here. This neutral sphere, this neutral sphere right down here has equal numbers of positive and negative charges. Like they're not drawn in there, but we could say that there are a bunch of pluses, 4 pluses, and 4 minuses. And they're evenly distributed around, right? They balance each other out. However, If I bring something really positive near it, like this rod, there's a lot of positive in that rod. And so since opposites attract, all of the negative charges in the ball are going to want to come over towards the positive rod. They're going to be attracted over there. That leaves the ball what we call polarized, where part of it is really negative and the other part of it is really positive. As a result, the sphere and the ball, or the sphere and the rod, are attracted to each other because the positive and the negatives attract. Great. So that's the concept of polarization. So let's do a little stop and think. An electroscope is charged by touching it with a positive glass rod. The electroscope leaves spread apart and the glass rod is removed. Then a negatively charged plastic rod is brought close to the top of the electroscope, but it doesn't touch. What happens to the leaves? Okay, so here's a picture of an electroscope. It's basically a big metal ball with a rod attached to it and then two leaves. And those leaves can move, they can vibrate, and so they'll get closer or further apart depending on how they're charged. So we start by touching it with a positive glass rod and they spread apart. Okay, so when they have a positive charge on them, it goes positive, 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 positive. So we charge it with that positive glass rod, and as a result, they move apart. Then a negative rod is brought close to the top of the electroscope, but doesn't touch. Okay, so when the negative rod's brought close, right, here's my negative rod right there, negative, 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 all the positive charges are going to move towards the negative. We're going to polarize this thing. So the positive charges are going to come up here. That means this positive charge and this positive charge are all going to be pulled up here. Now the leaves are left as less positive. So they are going to end up getting closer together, right? Because the positive charges are no longer there. They become more neutral. And so they'll come closer together. So that would be A, the leaves move closer together as the positive charge polarizes up closer to the negative rod. Great. Okay, let's talk atoms. So charges come from subatomic particles. And the subatomic particles that we look at are protons, neutrons, and electrons. For our purpose, we don't need to pay attention to neutrons because they are neutral. They do not have any charge. Protons have a positive charge, and that's found in the nucleus. And electrons have a negative charge, and that's found outside the nucleus in the electron cloud. So here is a diagram of a normal atom, a neutrally charged atom. The size is really exaggerated here. Atoms are crazy, crazy tiny, and then the nucleus within the atom is insanely small within it. So just so we can see it, they've made it a little bit bigger, but there are 5 positive protons and 5 negative neutrons, so that balances out to neutral. If I take one of those neutrons away, I still have the 5 protons, but now I only have 4 electrons. So that's an extra positive. So this is a positive ion. It has an overall positive charge because there's less negative and one more positive. If I added an electron to my normal neutral atom, now I've got 6 electrons to balance out my 5 protons. That's an extra negative. So now it's a negative ion, right? The extra electron gives it a negative charge. Okay, so charge itself. We use the abbreviation Q for charge. So the variable that we're going to be using is Q. The unit of charge is called a Coulomb. And an electron and a proton both have a set standard charge. And that set standard charge we call E for the charge of an electron. And it is 1.6 times 10 to the 19th coulombs. Just to be clear, we can't do fractions of an electron's charge because an electron either exists or it doesn't exist. It can't half exist. So you can't have 2.5 electron charges. We can't have 2.5 E, but we can have 2 E or 3 E, right? Because they're a thing. they're a quantum thing, meaning you have to count by whole numbers. So it's like people. You can't have 2.5 people. You can have 2 people or 3 people. So the charge there is listed in this table, and then the mass is also listed. You can see that we're looking at very, very, very small quantities. The mass of a proton, 1.67 times 10 to the 27th kilograms. The charge, 1.6 times 10 to the negative 19th. So these are 0.00000000000000, et cetera, et cetera, et cetera, et cetera. Very small. All right. Let's come back up and take a look at what we can do with some of those charges. So one of the things that we can do now that we know atomic structure and charges is we can make bonds. And one of the type of bonds that are charge related and really polarization related is hydrogen bonds. So here's a diagram of water. In water, there are 2 hydrogen atoms and 1 oxygen atom. The electrons spend more time over in the oxygen side. The hydrogens don't have the electrons as often. So the hydrogens become slightly positively charged, right, through polarization, and the oxygen becomes negatively charged. What that means is that when they bond, the negative part from the oxygen can make a loose bond to the positive part of the hydrogen. And then the positive part of this hydrogen can make a bond to the negative part of that oxygen. And this is why water sticks together, why you can have like a droplet of water, because the water holds together through these hydrogen bonds. Another place where this occurs is in DNA base pairing. So DNA sticks together. You know that DNA is a double helix running right through here. You have 2 strands running through, and those 2 strands are held together through the bonding between guanine and cytosine and thymine and adenine. Those are the bases in DNA that code for various traits. So when they bond, they are bonding between hydrogen bonds. So like a hydrogen bonding with an oxygen right there, I believe. Nope, hydrogen and oxygen is right there. Hydrogen to nitrogen is there. So you can see that they base pair. There's 2 base pairs, 2 hydrogen bonds between thymine and adenine, 3 hydrogen bonds between guanine and cytosine. All right. So let's go through and rank in order from most positive to most negative these charges. All right, so proton, that is positive, and it is +1, right? Electron is negative, so that's -1. 17 protons and 19 electrons, that means there are 2 extra electrons, so that's -2. 1 million protons and 1 million electrons, those are all going to cancel each other out. So that is net neutral, right? 0. And then a glass ball missing 3 electrons, that's -3. So that's +3. So from most positive to most negative, that would be, let's see, QE is the most positive, and that's going to be more positive than, so that one's good, A, QA, and that's going to be more positive than neutral, QD, which is going to be more positive than -1, QB, which is going to be more positive than QC, so that would be the most negative, at -2. All right, so let's talk about the relationship between charges. So we can find the force between charges using something called Coulomb's law. Coulomb's law states that the force, an electric force between charges, so I'll put a little E in here, force electric between charges, is equal to the electrostatic constant, K, times the first charge times the second charge divided by the distance between them. So K, Q1, Q2 over R squared will give you the force between them. And the electrostatic constant is 8.99 times 10 to the ninth Newton meters squared per Coulomb squared, or we're just going to round it to 9 times 10 to the ninth Newtons meters squared per Coulomb squared. Now you might notice that this formula looks really, really similar to one that you've seen before. It's almost identical to the force of gravity. Remember, the force of gravity was big G m1 m2 over d squared. So that was gravitational constant, mass over the distance between the two masses. This is the same thing, but it's using charges and an electrostatic constant instead of masses and a gravitational constant. But the force between them is exactly the same. Gravity works on a gravitational field, charge works in a charge field or an electric field. Otherwise, exactly the same. Okay, so let's talk about that. Let's try to add some electric forces in 2 dimensions. So I have 3 charged particles with Q1 equals negative 50. There you go. Q2 is plus 50 and Q3 is plus 30, and all of them are nanocoulombs. So a nanocoulomb is 10 to the negative ninth coulombs, right? So I'm going to take all those numbers times 10 to the negative ninth. What is the net force on charge Q3, so that's this one, due to the other 2 charges? Okay, so for each of these other 2 charges, first, I would say the charge is going to be on here, so I could draw those charges there. The positive one here, positive, positive, are going to repel. So this one is going to be pushing this charge directly away from itself. The negative and the positive are going to attract, and so the negative is going to be pulling it directly to itself. And this one's 50 and this one's 50, so those should be equal to each other in magnitude. So if I can find one of them, I'm going to know the other one. And then this is 5 and this is 5 centimeters. So then the distance between them, boom, boom, like that distance is going to be the hypotenuse of 5 and 5, right? I have 5 squared plus 5 squared would give me that distance. All right, so let's start there. So first, I'm going to find the magnitude of that charge, and then I'll work my way from there. So let's start by figuring out the distance, because I know that I need to use the force equals K Q1 Q2 over R squared. In order to find R, I know that it's 5 centimeters on one side, 5 centimeters on the other side, and the total distance would be the hypotenuse. That would tell me A squared plus B squared equals C squared. Now 5 is in centimeters, and I'm going to want it in meters. So that would be 0.05 squared plus 0.05 squared equals C squared. And then I'll take the square root of the whole shebang to get me C by itself. So the distance, the radius, or the distance between them, is going to be equal to 0.05 squared times 2, and then take the square root of that, 0.0707, or 7.07 centimeters. And that's 5 square root of 2, right? 5 centimeters times the square root of 2. So that would be in meters. Now I can plug that value in to find the total force. So the force is going to be equal to K, which is 9.0 times 10 to the ninth newtons meters squared per Coulomb squared times the 2 charges. So the charges that I'm looking at in this case are between Q2 and Q3. So that'd be 50 and 30. Now, if I did it the other way between Q1 and Q3, it would also be 50 and 30. So in each case, the magnitude is going to be the same. So I'm just going to do it once. But the first charge is 50 times 10 to the negative 9th coulombs, because a nanocoulomb is times 10 to the negative 9th, times 30 times 10 to the negative 9th coulombs. And all of that over 0.0707 meters squared. Okay. So 10 to the 9th and 10 to the negative 9th are going to cancel. So I'm left with 9 times 50 times 30 times 10 to the negative 9th. 9 times 50 times 30 is 113,500. So that's 1, 2, 3, 4, 10 to the 4th plus 10 to the negative 9th gives me 1.35 times 10 to the negative 5th. Okay, over 0.0707 squared. It's 5, basically, 5.0 times 10 to the negative 3. 1, 2, 3. Yeah, okay. And that'll be in newtons. Okay, so that's going to end up being 1.35 divided by 5, 0.27, 0.27 times 10 to the negative 2, which would be 0.0027 newtons. Okay, so that is the total force going off in these two directions, 0.0027 newtons going off there. Now we're trying to figure out the net force on charge 3. So when I take these two and I'm going to draw them out so that I know that I've got those arrows, but that is, if I draw the components, each of them have these components, a horizontal and a vertical component. And since the two legs are the same, I know that that angle is 45 degrees. So this angle in here is also 45 degrees. So at a 45-degree angle, I've got the vertical and the horizontal. And then on the other side, I've got the horizontal and the vertical components. And so these vertical components are going to end up canceling each other out. Those are going to be the same magnitude. So all I'm left with is the two horizontal components going to the left. So because I have those two horizontal components going to the left, I just need to find what that value is. So to find the horizontal component, I know that my overall total is 0.0027. So I'm going to do 0.0027 newtons times cosine of 45. And that'll give me my horizontal component. And that's 0.0019, 0.0019 newtons. Okay, so now I know that the horizontal component is that much, but I have two of them. I have one over here in green, and then I have one over here in red, because I had both of those arrows going there. One arrow there, one arrow there. So I'm going to multiply that by 2 to get me my final answer of 0.0038 newtons to the right. So the total force would be 0.0038 newtons to the right, okay, or in the negative x direction. Nope, not the right, the left. It's the left. Tough when I can't even get my left and my right correct. All right, it is to the left. There we go. All right. Nice. So we are able to go to our next piece and to do a little stop and think before we start talking about electric fields. So we'll do right here. Charges 1 and 2 exert repulsive forces on each other. Q1 is equal to 4 times Q2. Okay, so 1 and 2, good. And 1 is much bigger, sorry. Yeah, 1 is 4 times bigger than 2. Which statement is true? The force of 1 on 2 is greater. Oh, okay. So which is greater, the force or the force? Well, remember, every force has an equal and opposite force, right? So if 1 is pushing really hard on 2, then 2 must push equally hard back on 1. So that would be B, based off of Newton's third law. Every action has an equal and opposite reaction. Cool. All right, and we're going to pause there and then come back for part 2. And in part 2, we will talk about electric fields. All right.